So we're back after the lunch break, continuing our tutorial series on pseudo-Boolean solving and optimization. Before lunch, we talked about decision problems, first SAT, and then the more general pseudo-Boolean decision problem, or decision problems really for 0-1 integer linear programs. Now, after lunch, we're going to start looking at the optimization problems. And there are many different ways of talking about optimization problems. So one way, the classic way, is MaxSAT. So then you still have a CMF formula, and normally, like all these constraints in SAT, all constraints are hard. You have to satisfy all of them. In MaxSAT, some of them are suddenly soft, and you can violate them if you're willing to pay. Okay, but of course we want to satisfy as much as possible, or have as small a penalty as possible. You can do the same thing, but for a pseudo-Boolean formula, and then you get weighted Boolean optimization. Another setting is to be even more refined and say, sort of MaxSAT sort of says either I'm satisfied or you pay. Okay, you can even be, but you can, we can talk about it and be even more refined and say how much you're going to pay depends on how much I like your assignment or how much I do not like it. And I'm not sure that's exactly the full formal definition, but that's sort of getting into weighted constraint satisfaction problems, kind of, where you have constraints and you have a sort of, for every assignment, you have a price. And I think it's sort of, a hard constraint would probably charge infinity for something that you really doesn't like, and 0 if it's super happy, but it can be in between. And then there's pseudo-Boolean optimization, or 0-1 integer linear programming, which is basically you have a bunch of 0-1 integer linear inequalities and you want to minimize. Remember, we always think about minimization. We want to minimize a linear objective subject to satisfying these constraints. And this is the view we'll take. We'll think of all our, and this is also without too much loss of generality, as we'll talk about. So in general, we'll think about minimizing a linear objective subject to a 0-1 integer linear program. Okay, but we'll talk about how MaxSAT is actually this problem in disguise. And maybe you know it already. If you don't, then you'll know it in 5 minutes. Okay, that's the plan. And just to recap what we saw also before lunch, of what might these problems look like. So one first observation is that our favorite NP-complete problems are pseudo-Boolean optimization problems. I have an undirected graph with vertices v, edges e. I have a weight function for vertices telling me how much they're worth. And I want the clique that has the maximum weight. It has to be a clique, so if 2 vertices are not connected, then I can only pick one of them. But subject to this, I want to maximize the sum of the weights of the chosen vertices, but now I insisted on minimization, so then I just put the minus in front. This stupid thing, right? A maximization problem is just minimizing the negation of the object. And then we also have vertex cover, which is a true minimization problem. I want to choose as few vertices as possible. However, for every edge between u and v, at least one of the incident vertices u and v have to be chosen. It has to cover, like a vertex cover is covering the edges. I always had problem remembering this. So like a vertex cover is what it's not covering, namely what the edge is. That's how I try to remember these times. Nowadays, and somehow miraculously, I got to be a professor without remembering this fully. So there is hope for everybody. A more general notion than vertex cover is, if you think about it, edges are just sets, right? Sets of size 2. I could have any collection of sets from some universe U, and where the elements C in the universe have weights. And a vertex cover happens to be choosing a subset of the universe that hits all the edges. In general, I can minimize the weight of a hitting set that intersects all the set in my collection. Okay, and just to be sure, if you have any questions about this, like, we're going to see this problem again. Okay, so we want to be sure that we understand what this is. So, but here is, again, as a 0-1 integer linear program, or as a pseudo-Boolean optimization problem, they're very, very hard to distinguish. But of course, again, as I told you before, a SAT person will say this is a pseudo-Boolean formula. Someone in operations research might refer to it as a 0-1 integer linear program. They're the same. And again, so our problems will be optimizing, minimizing a linear function subject to some constraints. And actually, a lot of the time, even having a CNF formula as constraints is enough. And this formalization, like without any loss of generality, this formalization, minimizing a linear objective subject to CNF formula, this is exactly the same thing as a MaxSAT problem with hard and soft constraints. And I'll explain this to you in a few minutes if you haven't seen it before. When I set up the problem and define, so a lot of the techniques that, so again, we want to solve 0-1 integral linear programs, we want to optimize, but we're coming from the SAT side. So we're going to try to use SAT-based techniques, and the SAT-based techniques are typically the ones that come from MaxSAT. So that's why we'll make sure to explain how MaxSAT solving works. And then, as we already saw before lunch, there's sort of an obvious algorithm, which is just find a solution and ask for something better until you cannot find anything better. We'll talk about so-called solution improving search, which is sort of, you're going from the SAT regime until you finally cannot find anything better, and then you're unsat. So that's sort of SAT unsat search. But there's also other more powerful techniques where you do exactly the opposite. You try to shoot for the stars and find a fantastic solution, and then you realize it didn't quite pan out. And then you try to find a slightly less, but still fantastic solution, and that still didn't pan out. So you're like unsat, 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 until you finally manage to find something, and then you know that's optimal. Okay, and we'll talk about such unsat SAT search, which is a very important notion is so-called core constraints, and we'll try to make sure that we know what core constraints are. That's sort of the core of this talk. And then, of course, we'll talk about some open problems. And I'll try to weave some open problems into the presentation also. And, since this is November 5th, I, of course, have to say that I will also try to do the weave. And, we'll see if I'm more or less successful than some of the US presidential candidates at this and making everything come together at the very end. So, and you should, again, I'm getting a little bit too few questions. That's making me a little bit worried. So you can view that as criticism. And the way you can deal with this is you can ask more questions. But, I guess if the presentation is like truly amazing, then just, everything is crystal clear. I try to make sure that everything will not be crystal clear any longer. So hopefully it's really not confusing enough and enough typos that you will have to ask. That's my goal. Okay, weighted MaxSAT. Let me give you like the classic weighted partial MaxSAT definition, which is probably what you find in the textbook and what I think theoreticians think about. So there are soft clauses, C1 up to C lowercase m, and they have weights, W sub I, and throughout this talk now, W sub I will be a positive integer, which is some kind of weight or penalty. And then there are hard clauses, C lowercase m plus 1 all the way up to C capital M. And those are just have to be satisfied. So the goal is to find an assignment row. Remember that row is typically an assignment, and row has to satisfy all the hard clauses. So saying that row assigned all the hard clauses to true, and then you want to maximize the number of soft clauses that you satisfy. Okay, that's the classic definition of MaxSAT. And now I want to argue that this is just minimizing a CNF subject to linear objective. We'll get there. First, the first step that we have to take, which is sort of that happens very quickly. I don't know how many of you have been to MaxSAT talks, but you have the first slide, and then immediately MaxSAT turns into a minimization problem. And if you're not strong, this might be slightly confusing, but the reason MaxSAT is really a minimization problem is instead of maximizing the weight of the satisfied clauses, we will minimize the penalty of the violated ones. Okay, so this feels good, so it feels safe. Now we're back in our minimization setting. And this is also nice because now the hard clauses get a very natural weight, right? They get weight infinity. Okay, and I'm trying to minimize the sum of the weights of violated clauses, and it's kind of clear that, well, as soon as I screw up a hard constraint, I have infinity, and we might as well go home. Okay, makes sense? And also, sometimes the notation is used that you write parenthesis clause sub W. That's now the weight of a soft clause. Okay, and if you want to stress that a clause is hard, maybe you write C sub infinity. Okay, are we happy with MaxSAT? Okay, now we want to see how this is in fact a 0-1 ILP, and I'll do it by example. So here we have not X is a unit clause of weight 5, Y or not Z, soft clause of weight 4, not Y or Z, soft clause of weight 3, and then we have 2 hard clauses. Now I'll view this first. We know that clauses are just sums of literals greater or equal 1, right? But in addition, for all soft clauses, I now introduce a new fresh variable B1. I add it to the clause, okay? And that variable, that literal, will only be in that clause and nowhere else. Okay, so now suddenly all the soft clauses are actually super easy to satisfy, because clause 1 is satisfiable by B1, clause 2 is satisfiable by B2, and clause 3 is satisfiable by B3. But obviously now I'm cheating, right? If I'm choosing B1, I'm not really satisfying not X, so I should have paid 5. And if I'm choosing B2, I should have paid 4, but that goes into the objective. Okay, so I have these so-called blocking variables, and then I just collect all the sums in the objective. And I'm doing this for pedagogical purposes. If you actually did this in practice, you would not introduce this B1 guy, because you realize I might as well put X in the objective directly, right? That's like a minor point, just if there are any MaxSAT purists in here, you see I screwed this up. But modulo this, like any SAT solver, MaxSAT solver that I know of, when it gets this is sort of in the Dymax MaxSAT format, it immediately gets translated to this. And this is all that we're going to think about. Okay, except that maybe we think about them as clauses if you're a MaxSAT solver. But you immediately do this blocking variable transformation, where the BI are, again, blocking variables or relaxation variables. And this is such a given that usually, like, in several MaxSAT talks, they won't even say this. Suddenly the blocking variables are just appearing somewhere, and you sort of have to know that this is what they've done, because everybody does it.
Okay, let me correct it and interact a little bit, because you say we don't. So some old range and bound solvers might not do this, because they want to preserve the original soft clauses to apply something like MaxSAT resolution or things like this. So indeed there is some solvers that don't do this, but not the current state-of-the-art solvers.
Okay, good. I stand corrected. I should have said like the current state-of-the-art. I think it's fair to say does this.
Yeah.
But of course, you don't necessarily have to do this. And when you think about like methods of reasoning, you might. I mean, there are certainly proof systems operating with hard and soft clauses. These kind of. But again, for state-of-the-art, like if you're picking the I don't know what, the top 3 or top 5 in the MaxSAT
all the ones that
evaluation,
yes,
they will sort of immediately do this. Except again, I think it's also fair to say probably most of them will not transform unit clauses. I think another slightly annoying thing is, of course, is this variable now negate? Is it unnegated or negated? I think this depends a little bit, and this is a confusion no end. For me, they're unnegated. Okay, but you could have them negated, and then you would just negate here instead. And if you look at this, just to make sure we're on the same page, we have to satisfy these 2 clauses, but we can violate. Turns out that we can get away with, this is unsatisfiable, but we can satisfy everything except the cheapest clause by setting X and Z to false and Y to true. Okay? So unless I screwed up, this is something you should, maybe this is one of the typos I talked about, right? But I think this is correct. So this, and now I argue that I've showed you from MaxSAT, this is obviously a 0-1 interlinear program, yes? Okay, but you can also go in the other direction if you allow yourself to have MaxSAT but with pseudo-Boolean constraints, which is again weighted pseudo-Boolean optimization. In the other direction, the translation is kind of obvious. So if I have a pseudo-Boolean optimization instance, I'm minimizing my objective. Again, I'm assuming normalized form here so that all the WIs are positive, and I can play with the literal so that this is the case. And then I have a bunch of hard constraints. Well, I just say that all the hard constraints are indeed hard. And then I take all the literals in the objective, I negate them and turn them into soft clauses, and the coefficient becomes the penalty. Right? So from now on, sort of, they are really, MaxSAT, 0-1 interlinear programming, weighted Boolean optimization, it's all the same. I can't distinguish them. is my philosophical take. Or if I could, then there is some way of trying. I mean, I'm not saying that it might be more convenient to think in one setting or the other, and in fact, we're going to think a little bit about both, but like our main setting are 0, 1 interlinear programs. Okay, and there are 4 different flavors of MaxSAT. I mean, partial max.
Also, slide before, those constraints on the pseudo-Boolean side, they don't have to be clauses if we can.
Yeah, so again, like these constraints will be the same as this, but if there's general pseudo-Boolean constraints, then this is then this would be a weighted, right? I mean, this is a weighted Boolean optimization instance. If you have pseudo-Boolean constraints, if they happen to be all clauses, then we think of it as a MaxSAT. But MaxSAT is a special case of weighted Boolean optimization.
Yes. Okay.
Okay. So it's just I'm not exactly sure why this terminology, but it seems to be like it just exists in the literature.
Okay.
If you have both hard and soft clauses, then it's a partial MaxSAT problem. MaxSAT traditionally has only soft, and then you can have unweighted or weighted. Unweighted is where you think of like all the soft clauses have the same weight, and then you realize without loss of generality they all have unit weight 1. Weighted MaxSAT is different soft clauses cost differently. Okay, so in principle you now get 4 different subproblems, and now I'm gonna make a statement again, and let's see if we need to refine this a little bit. But I would say that most, not all, but again, if you pick like a state-of-the-art solver, most of the time, without too much loss of generality, you're solving weighted partial MaxSAT, which is the most general one. There are sometimes techniques that sort of are easier to describe, say in the unweighted setting and so on, but most of the time, and you maybe have to work a little bit, we'll see a little bit of this maybe later, but most of it, my impression is that mostly you solve like, you know, weighted partial MaxSAT, because you might as well do it. And you don't have to pay any extra to deal with the most general setting. How do we do this? I already said a little bit. I'm going to talk about 3 different approaches. Linear search, going from SAT to unsat, also called solution improving search, or sometimes model improving search. Then I'm going to talk about so-called core-guided search and implicit hitting set search. But again, I'm going to assume that we've done this transition with blocking literals so that we're minimizing an objective subject to a collection of pseudo-Boolean constraints, which might or might not be clausal. Importantly, I'm not claiming, I said main approaches, I hope this is true, I'm not claiming that this is an exhaustive list. In particular, one thing that I hope we will hear about tomorrow or on Thursday, both tomorrow and on Thursday, right?
Yes.
Kind of, is doing branch and bound within a MaxSAT setting. Okay. Okay, and let's talk quickly about linear search, because it's sort of so straightforward. I think this is what we would all come up with as our first approach. Again, the setting for now is going to be like whenever you see WILI, summing from I goes from 1 to n, or even without the n indices, that's just going to be my objective. We want to minimize it. And we have a bunch of pseudo-Boolean constraints. This will be F typically, and the individual constraints are C1 up to Cn. So we can do the following. Just set my best solution so far to be the empty void. And then just run a SAT solver or a pseudo-Boolean solver. And if the solver returns unsatisfiable, then you say, sorry, this was unsatisfiable in the first place, and terminate. And otherwise, you found a solution, and you update row best to be this solution. Then you evaluate how good it is. You plug row into the linear inequality, and now you add a so-called solution improving constraint or objective improving constraint saying, I want one better than this. And then you start over and run your solver again. And now either you're going to get MaxSAT, in which case row best is the best one, or you will find a better one because you've added a constraint enforcing that you need to find something better. And just to make absolutely sure that we're on the same page, how might this work? Well, here is, we're going to have like a toy example with the objective x1 plus 2x2 plus 3x3 all the way up to 6x6. It's kind of an easy objective to remember. And we have a formula f that I'm not really telling you what it is. And suppose we just run it and it returns that, well, you can set everything false except for x4 and x5. Okay, maybe that's what's happened. What do I know? And then we just evaluate this and we realize that, well, this gives an objective value of 9. So then we somehow say that, could you please give me something of value at most 8? And really here you realize, how would I do this? We'll have to talk about this a little bit. In a MaxSAT solver, we need to think. In a pseudo-Boolean solver, we would just add this constraint, right? This is sort of just another constraint. We could totally do this. In MaxSAT, we'll have to talk about it a little bit. Okay, so now we run the solver again, and now it figures out that, well, you can get by with setting everything to false except x2 and x4 maybe. That clearly cost us 6, so now you ask for a solution of value at most 5. And now the solver says MaxSAT, say, and then I claim that we know that 6 is the optimum. Okay, so we're going to run other algorithms on this toy problem, and hopefully it will give us the same answer. Let's see. Good.
I have a question.
Yeah.
When you say that solver run again on F, you mean that you completely restart the search. You don't just backtrack trying to find a better solution than the one you found.
Oh, in practice, you would probably keep, like if you've learned tons of constraints and stuff, you know, let's keep them. That you will have a stateful solver.
Okay.
Makes a lot of sense.
You restart at the trade is completely empty in the beginning. You have no assignment and you begin the search with the extra constraint.
Yeah, I mean, yes, I think that's the, yes, because, yeah, let's think about it that way. I mean, these are, again, things you can play with, but you're going to restart sooner or later anyway.
Okay.
So, yeah. The key thing is like adding this solution improving constraint. Again, this is the vanilla, but well, actually, I'm getting to like, how would you actually do this in practice? Probably not like this. So the first thing I said, this solution improving constraint, you need to encode it somehow. And in fact, there's a whole literature on translating pseudo-Boolean constraints into CNF. This is like a research area. For this setting, I think the most sophisticated encoding is the dynamic polynomial watchdog encoding. And that encoding also gives you, there will actually be not pure linear search, but sort of in this encoding, you will have like, how would you say, there are like two different phases. First, you try to get the solution roughly right within a big power of 2, and then you'll do linear search within that interval. So there's like a linear search over rough values and then more fine-grained linear search once you pin down the right interval. There are all kinds of things you can play about. And they're pulling all kinds of very interesting tricks with these encoding also. For pseudo-Boolean solvers, why care? I mean, this is already a perfectly fine constraint. So I just add it, and like implementing solution improving search in a pseudo-Boolean solver is trivial. So that's nice. But one thing that is not so nice is, again, the dynamic polynomial watchdog encoding, for instance, it will give you access to lots of auxiliary variables that mean very, very interesting things. For instance, you will have variables for all of these values of powers of 2 during the coarse convergence phase. And the solver can speak about things like, you know, I think the solution is larger than this power or 2 or something else. So you can build like more complex statements. And if you don't have these auxiliary variables, then you can't build these complex statements. Okay, so it's a little bit incomparable. One other thing is, if you're a theoretician, so like linear search, that sounds really dumb. I mean, we all know that binary search is so much better. Isn't that like the first lecture in Algorithms 101? First, we tell the students how linear search works, and then we tell them, please don't ever do this again. Right? But here it actually seems that linear search is better. And when I try to understand why and talk to people who supposedly know this, I think there are several reasons for this. One is that, well, linear search is bad when you increase the value only by 1. But if you actually run a linear search SAT on SAT solver, then typically you'll get much larger jobs in practice. So like you won't find a solution that is just one better, you'll find a much better solution most of the time. And also binary search kind of silently assumes that all search calls are equally expensive. Whereas for a solver, typically SAT calls might be very cheap. Unsat calls could be super expensive. And if you're doing linear search SAT on SAT, then you know you have most of the SAT calls will be very cheap, and then at the very end you have an expensive unsat call. Whereas if you do binary search, then potentially every second call on average would be very expensive. Okay. Still, I'm not sure. I mean, I think it would be worth. Suppose that you have a solver that is a little bit better than at unsat than a SAT solver. Maybe it would still be worth investigating this in more detail. I don't know. So from linear search, you can get a decent solution quickly, even if it's not optimal. And in a real world setting, there's something that's called anytime solving. And anytime solving is basically, please solve this problem for me, but I don't have all the time in the world. So I'll let you run for, I'm not sure. You know, I'm going to make a coffee, please run. Meanwhile, and you know, maybe I'm back in 5 minutes, or maybe I met someone in the coffee room and then we had a half an hour discussion, but when I'm back, I need an answer, and then I'll tell you. And then an anytime solver gives you at that point the best solution it has. Okay, and linear SAT on SAT search has nice anytime properties because at all times the solver has the current best solution and can give it to you. However, it has no idea how good this solution is in general. Like you have no idea whether you almost nail it or whether you're ridiculously far from it. Okay, so this is what I want to say, I think, about solution improving SAT on SAT search. So now let's move on to what I've chosen. This is not established terminology, I should say, but I called it like core-directed unsat SAT search because I'm going to talk about. It would have been very natural to call this core-guided search, except that one of the approaches for core-guided search happened to be called core-guided search. So that's why the more general term, I'm saying directed instead of guided. Okay, and a very important notion for this is the notion of running a solver with assumptions. Let me tell you what this means. This is the following setup. I have a CNF formula or maybe a pseudo-Boolean formula F, but I also have an idea of what a solution might look like. For whatever reason, I like the partial assignment sigma. It's a nice assignment. Okay? And running the pseudo-Boolean solver on F with assumption sigma means the following, that I want either, I do the following, that the solver gets sigma, and whenever it wants to make a decision, it checks if there is a variable in sigma that has not been decided. If so, it makes the decision. So like sigma is a list of pre-made decisions, and you should not do anything else, no other branching decisions until you've emptied sigma. That's the deal. And typically we think of sigma as being ordered also. But when all of sigma has been taken care of, then you switch back to a standard decision heuristic. Make sense? Okay, but now what can you expect the solver to return? Well, either it finds a solution, and if so, by definition, by construction, this will be a solution extending sigma, yes? Otherwise, we want the solver to return unsat, except it could not possibly return unsat because maybe the formula is satisfiable. The only thing we know is that, well, you couldn't extend sigma to get a satisfying assignment. And what the solver will return is an explanation, and this is called the core constraint, saying why sigma is too much to ask for. Okay, and you should think of this as a disjunction. We'll make this slightly more refined later, but I get back a disjunction over negated literals in sigma, saying that you have to give up on one of these at least. Okay. This is what running with assumptions is. Okay, how do I get this explanation? Good news, you don't need to do anything. You just run conflict analysis with a very, very minor fix. Okay, so here's the precondition. We run the so-called decision learning scheme, which you might remember I told you that decision learning scheme is very old, from 1977. Comes in handy here. The precondition is that we have a clause database, we have a trail, a partial assignment row that has led to conflict. Okay, and now I run the so-called decision learning scheme. It's standard conflict analysis, except for two things. First, I set row des to be all the decisions. Just to remember those. I mean, I know which ones are free branching decisions. And I will run my conflict analysis not until I have a nice constraint, but until row is completely empty. Okay? And when this is already in a pseudo-Boolean setting, when I do my reduction step, I sort of, even if I've almost emptied all of row, I still keep my decisions. So like when I'm checking whether something is still conflicting, I'm always keeping the decisions. So this is different from before. But the red stuff is like basically if you have this is not how I should say, this is not how the decision learning scheme is implemented in rounding set, for instance. It probably is how it should be implemented. But really, like if you have a decision learning scheme, I'm not saying that this is the most efficient way of implementing it either, but basically you only need to check what the decisions are, change your termination criterion from first UIP to this, and when you're checking whether something is violating, keep the current assignment, but also all decisions made at any point. Never throw those away. Okay, and then what will you get? Well, you will get, it's not so hard to see, maybe after a few minutes offline, that now the return constraint that you learn will be violated by only decisions. Okay.
Something I don't understand is that row deck contains all decisions in row.
Mm-hmm.
So when you do row union row deck, it's always a row deck at the end.
No, all the decisions, but not all the propagate. Remember, there are decisions.
Okay, only
those are free branching decisions.
Okay.
Yeah, good, thank you. So yeah, when I say decisions, these are these branching decisions. Propagated assignments are not decisions because I don't get to decide those. Those are forced choices for me. Okay, makes more sense now?
Yes.
Perfect. Yeah. So that is why in the end, sort of, think of sort of when you're doing the final conflict analysis step, if you will, when you're actually emptying row, then what you will get is something that is conflicting only with respect to the decisions made. And if this was CDCL conflict analysis, then an invariant would know, you would actually know that the constraint only contains a subset of the decision variables. The way I've written it here, strictly speaking, you don't have that guarantee for pseudo-Boolean conflict analysis, but it's easy to enforce, right? If I have a learned constraint that is violated by the decisions only, then I can weaken away all unassigned literals and still have a violated constraint. So you can think of this as I'm getting back some kind of clause or pseudo-Boolean constraint that is only violated by the decisions. Okay, or the decisions only are sufficient to violate. Does it make sense? Okay, so so suppose just to see, already here we have the first, now I'm doing the weave, okay? Suppose I have a bunch of assumptions, sigma, there are S of them, capital S of them. How would I do this for CDCL? Again, I run standard CDCL, but always the first capital S decisions come from sigma, and then I run CDCL. When do I know? But note that importantly, I don't run the decision learning scheme all the time because we don't think it's a good learning scheme. So I'm going to run my standard first UIP learning, and at some point I have to switch. When will I switch? Well, if I reach a conflict after at most S decisions, then I know that the only decisions made are the assumptions. So then I switch to the decision learning scheme and I'll get a clause consisting of assumptions only. Okay, that's how I know how to switch. In the pseudo-Boolean solving setting, it's more interesting. In fact, you can hit a conflict at level S sigma, which is S prime, which is significantly larger perhaps than S. But during conflict analysis, you can sort of crash through several levels. This is something that never happens in CDCL. It can happen in pseudo-Boolean solving. I didn't stress this, but it's like it's not only a theoretical fact. This does happen. Okay? So you can start, maybe you had 10 assumptions, you got a conflict at level 20, and during your conflict analysis, you suddenly realize that, oops, I reached level 10 now. Then you could actually, on the fly, during conflict analysis, although you haven't learned anything, switch right then and there. Okay, just let me continue, but change my slack computation and change my termination criteria. Or you can say, this sounds complicated. It will probably be costly to keep track of the level. So I'll just keep going until I hit a conflict at level at most S. And in fact, if you somehow work your way through all the way up to level S and then learn something and back jump, then at the very next step, you will detect the conflict that tells you for sure that you can switch on the decision learning scheme. Which one of these is best? We have no idea. Okay, but this raises, which I think we should have an idea, but we don't. But this raises the question, okay, but since you have this choice, I could also do another thing, right? I could switch to the decision learning scheme and learn something, and then I could say, actually, let me now try with let me add this thing that I learned and let me try my assumptions again. And see, maybe I learned something even, maybe I hit conflict at even earlier levels now. Maybe I should just keep going and not return until I see that my level drops again. I could I could keep learning these decision learning scheme constraints as long as the level shrinks until the level increases again, at which point I say, okay, here's the best score I have. Would that be a good idea? I'm not aware of anyone having tried. Maybe, maybe someone has, because in the SAT community, there's like smart people have tried lots of crazy things. In pseudo-Boolean solving, I'm pretty sure that nobody has tried. And it is kind of this whole question is a kind of thing that arises somehow more in a pseudo-Boolean setting, because it's there you realize that there is a choice in the first place.
I assume you were sorting assumptions by weighting the objective.
Yeah, well, that is something that the callee is responsible for, right?
Sure.
So this is not really, this is outside of what we're talking about now. But this is my response, but you're absolutely right that if I'm, okay, but you're like 10 slides ahead of me maybe at this point, but yes, like, I agree that if you're running with assumptions and you want to assume variables to the right values so that you get a nice objective, taking care of the heavy literals first sounds like a good idea. Yes. But right now we're just talking about this, like we have opened up the assumption solving box and are talking about that box. So note that the solver with assumption has no idea what an objective is. Like what you just said to me, I have no idea. Make sense? But just to stress here that there are questions here that we don't have good answers. Now let's talk about how we would use this. Okay. Again, we have the same objective, the same formula. What is core-guided search? Well, let me think of a MaxSAT instance and think of this blocking literal transformation. So actually think of the objective as being these relaxation literals for a bunch of soft clauses. Okay, are you with me? This is the translation we had before, right? So you want to see this? Here, so like think of the objective where you know that B1 is sort of related to clause 1, B2 is related to clause 2, B3 is related to clause 3. Then it's sort of, then you could think of the literals in the objective as clauses. Okay, so let's think like that. And let me tell you what core-guided search is. Now you do exactly opposite. You go crazy optimistic. You say, I believe that the value of this objective is 0. Okay, so you set all the literals in the objective to 0. That's your assumption, and you run the SAT solver. And now one of two things can happen. Either you're right, you get a solution extending this, and then we have solved the optimization problem. I think that's pretty clear. More likely, you get a clause back over assumption variables like L1 or something up to LK, where you say, well, you can't set all of these to false. This is what you'll get back. Like either you get SAT back or you'll get a clause over these literals that you assume to false, which saying, no, at least one of them has to be true. And remember now that these actually correspond to clauses. So this is like identifies a subset of soft clauses where you say you cannot satisfy both the hard clauses and all of these soft clauses at the same time. So the hard constraints together with these clauses, they form an unsatisfiable core, is the terminology. Okay? So we think of this as a set of core clauses, except from now on, they're not going to be clauses for us. They're just going to be literals in an objective, but we still talk about the core constraint. Okay? Yeah, so this, and then what, so here we'll talk about this more in a second, but what we'll do now is we'll basically introduce new counter variables that counts how many of these have to be true. How many do I have to give up on? Okay, so a variable zj will mean that at least j of these guys are true. And again, if you're in a CNF land, you'll have to encode this somehow. If you remember from before lunch, in pseudo-Boolean land, these are just 2, 0, 1 interlinear inequalities, right? And now, in some way, I actually rewrite the objective to take into consideration that I have to give up on at least one of these. And then with the rewritten objective, I then go maximum positive again and say maximum optimistic and say, well, except for this, I can do everything. Okay. And okay, so this is like the traditional description of core guided search. And you see it's kind of a linear search again, but now we're not going from SAT to unsat, but from unsat to SAT. Because the first time I get something that is satisfiable, then I know I have the optimum. How do I rewrite the objective? I use the so-called OLL algorithm, and it's fascinating. Apparently, nobody knows what OLL means, but it's called the OLL algorithm. Okay, so I'll tell you what the OLL algorithm is. What I will not tell you is what it means, because this I don't know. And again, as I told you, our view, we don't have any soft clauses with blocking literals. We just have an objective. Rewriting, again, we said these counter variable definitions, they will just be adding reified pseudo-Boolean constraints, which is very easy. And so in a pseudo-Boolean setting, core-guided search is basically just assuming that the objective can reach the best possible value. You derive a contradiction. If this is not possible, from this contradiction, you rewrite the objective, and then you try again. Okay. Interestingly, one question that I ask myself is there anything like this in operations research? I am not aware of it. And I think it could be quite fun. I'm jumping 2 lectures ahead of myself, but what would happen if you take like a good MIP solver and encode core-guided search on top of it? I think that would be fun. Let me now try to explain this rewriting, not by heavy notation. I'll do it by toy example. Okay, and maybe a little bit fast, but let's see if we can do this. Actually, let me also, one thing that I should have done from the start, I'm trying to time myself. Where are we? Good. So the same pseudo-Boolean formula, same objective. Here we are. So we say that the best possible value is 0, and that is achieved if all the x's are false. So we run the solver, and it says nope. And we get back a constraint over these assumption variables. And in general, in a pseudo-Boolean solver, this could be any pseudo-Boolean constraint, something like this. Okay. And then we say, here we get a little bit nervous, and we say that looks like an ugly constraint to me. Could we please turn it into a cardinality constraint? So I round it to a cardinality constraint. Do we have to do this? Not necessarily. That's a research question. That would be very interesting to look at. But what we do is that we round it, and you'll see shortly why. So now I introduce new counter variables, y3 and y4, and the meaning of y3 will be that 3 of these variables are true, y4 will mean that all of them are true. So I will somehow make sure I could, in principle, this is not exactly the way it is done, but I could just throw in this equality, and this is okay because these 2 variables are fresh. And then I can also just say that y3 is larger equal y4. And with these 2 constraints, that will make sure that yj means exactly that at least j of these variables are true. Does that make sense? Okay, so I just add these to my solver database as new constraints. Okay, done. Now I can take this constraint and multiply it by 2. Why by 2? Well, I look at all of these variables, I look at them in the objective, and I pick the smallest coefficient, and this is the one of x2. Okay, so I multiply this whole thingy by 2 and simplify it a little bit, and I realize that 4 plus 2y3 plus 2y4 minus 2x2 plus 2x3 plus 2x4, minus 2x5, that's 0, right? Well, if this is 0, I can add it to the objective, I guess, without changing the objective, yes? So let me do it. Adding this to this, I get a new objective, and note that actually x2 cancels. And x3 and x4 and x5 get smaller coefficients now. x1 and x6 are unchanged. I pick up 2y3, 2y4, and a constant 4. And this objective is equal to this objective, right? Because I only added an equality. So, but looking at the rewritten objective in this way, we see that the best possible value is 4. Do you agree? Okay. So now what I will do, I say, okay, I guess the best I can get is 4, but I would get it if all of these guys are 0. And now I just repeat. Okay. So let's do this. I run the solver assuming that all literals in here are false. It comes back to me, and now it gives me a clause that says that, sorry, x4, x5, or x6, either they are true, or if not, then you have to set at least 3 variables true in your previous score. Okay. And again, I know what to do, right? I introduce new variables that are counting how many variables here are true. I make sure that z2 greater equals z3 greater equals z4, so that zj really means what I want it to mean. And now I want to massage this 7a again. I look at what my coefficients are in here. I think the smallest coefficient is probably a 2 again. Can we see this? This is my new objective. x4 had a 2, and y3 also had a 2. So this is my smallest coefficient. So I multiply this equality by 2 and rearrange and get something that is identically 0. Add it to the objective. And now you see that, what do we get? What cancels now? x4 cancels. And y3, I guess, also cancels. And I pick up a bunch of z's. And I also pick up a constant 2. So now the lower bound is 6. So since this objective is equal to my original objective, I know that the best lower bound I can hope for is 6. Okay. Yes?
Is that actually implemented in rounding SAT?
I'll get to it.
Can you go back to the previous slide?
The brief answer is yes, but yeah.
Do you actually add to rounding SAT this definition, namely
No.
x2 plus x3?
This is actually one of this is. I think there are options for this. I would not do it this way. I'll get to it in a second.
Okay.
I wouldn't do it this way. I think you can force rounding SAT to do it this way.
Okay.
With the sum encoding or whatever it's called. Mark Vinils is nodding, so this is probably true. This is easier to explain, so that's why I'm doing it in this way. Okay, so now we know that the optimal value was 6, right? So now when we search for a solution with all of these literals to false, the solver had better say SAT, and it does. It gives us back this solution. And then by just some back substitution, well, under this assignment, The first equality that we had, the 4a, says that this has to be true. And this can only hold if y3 is 0 and x2 and x4 are 1. And then you see that this also satisfies the other equality. And I'm going a little bit slow, so I think I'll just breeze through this. Everything like this is online. And the end of the story is that we have now found an optimal solution, but we found it by going unsat, unsat, unsat until we finally were set. Okay. What this method gives us lower bounds quickly, and that helps us to cut off parts of the search space that where there are no solutions. The bad thing here, just as, I mean, for linear sat unsat, we had no idea how far we were from the optimum. Here, we have no idea how far we are from a solution. In particular, if you're in an anytime setting, then this algorithm is terrible, right? It will just say, I have absolutely no idea until it finally gives you the optimum. It's like, thanks a lot, pal. I mean, I would have, it would have been nice if you gave me something. And so it just has a lower bound. This might be interesting, but you don't know how good this lower bound is. And it's a natural question to ask, well, I'd like to have both upper and lower bounds, please. Can you somehow get this? Okay. So this is sort of vanilla core guided search, if you will. Now let's talk about how you would actually do this. I'll do this very quickly. Again, as for the other slides, all the references are at the end of the slides if you want to read up on this. So I'll just sort of mostly go quickly by example. Suppose you have an objective that looks something like this. x1, x2, x3 have fairly low coefficients, and then x4, x5, and 6 are heavier, and x7, x8, x9 are like super heavy. Okay? And you want to do core-guided search. If you assume all of these to false at the same time, and you pick up maybe you have to satisfy x1 or x4 or x7, that's not really very informative, right? Because it only gives you a lower bound increase of 1. So it would somehow make sense to just say, actually, let me see if I can get all of these red guys, the really heavy guys, to 0. But let me just assume those to 0 and see. If I get a contradiction already from these 3 assumptions, setting x7, x8, x9 to 0, that core will give me a huge lower bound increase. That's nice. On the other hand, suppose that assumption actually works out so that the solver gets me back a solution. Well, that's also pretty nice, because now I have suddenly a decent solution. I don't need to worry about all these heavy objectives, literals. Okay? And then, once you're done with these heavy red guys, you maybe assume both the red guys and the blue guys to 0. And again, either you get a core back, but then you get a core over fairly heavy guys. And if you get a solution, well, great. Then you know that you only have a very small range where you need to find the optimal solution. How do I do this stratification? Well, there's some formula for this. It's basically some kind of greedy thing that basically you start summing things up, and then when you detect that you sort of have a jump, you say that, okay, this is sort of one part of my stratification, and then you continue. And as I said, if you get a more compact core, if you only have assumptions over heavy literals, you get a more compact core, which will give me a lower bound increase that is better when you do this OLL rewriting. And otherwise, it's a win-win. You can also find a decent solution. Another thing, going back to our example, we had this linear objective. We assumed everything to false, and we got this core back, right? x2, x3, x4, x5. In general, this rewriting step that we then did, especially in the context of SAT-song, that's like a heavy step compared to extracting cores. So you want to sort of extract as much information as possible before doing the rewriting. Also, it's nice to see, especially at early stages, maybe there are several reasons why you can't assume things to false in the objective. And so one thing, if you extract these joint cores, you just say, okay, let me remove all of the variables in my core, but still assume the rest to false and run with that as an assumption. Okay. Maybe I will now pick up a second core over this variables only, and then I have another lower bound increase that is completely disjoint from the other one. There is something that is apparently even better than this that is called weight-aware core extraction, where you basically, you do the rewriting that we did before, and you only remove from the assumptions the variables that cancel in the objective. Remember, in our case, this first core that we rewrote, only x2 canceled, the guy with the minimal coefficient. So if you do weight-aware core extraction, you would immediately run the solver again with assuming everything to false except x2, without doing any objective rewriting. And this is apparently weight-aware core extraction is better than disjoint core extraction. And this gives me, yeah, more independent cores. So I increase my lower bound more, and I guess also I think for MaxSAT, like the rewriting step is a little bit cumbersome. If you're in a pseudo-Boolean setting, I'm not so sure about this motivation. But anyway. Another obvious thing that you could do, and this is maybe related to a question we had before lunch, suppose that I find a core like this, so AI Li greater equal A. One thing that I could do in both SAT and MaxSAT, in both MaxSAT and pseudo-Boolean solving, let me define a new variable that says, actually, maybe this is greater equal A plus 1 even. Okay. And then I run the solver with a single assumption where I say, no, this is not possible. In fact, this bound is tight. Okay. And now one of two things can happen. Either the solver says, no, this looks fine to me, and then that's a little bit disappointing. But apparently often what can happen, especially in a clausal setting, is that the solver says, no, this is not satisfiable. And then you immediately know that this core that you found, the degree of falsity was not tight, and you can bump it. And then you can see, can I bump it further? Another thing you can do if you have clauses is you can try to remove some literals and just assume the rest of the literals to false and run with those as assumptions in some way and see if I can somehow shrink the core. It's not immediately clear how you would sort of do core trimming for a general pseudo-Boolean constraint. I don't know if this has been tried. By the way, this is one thing that is not being done in RunNSat that we probably should do.
I have a question still to this. When you introduce these new variables, so
Yeah.
you never introduce, I mean, let's say you just have a sum, let's say you have a cardinality constraint only, you never introduce all of the y variables at the same time.
I'm getting to it.
So only one at a time, because the rest maybe you can add lazily or
Yeah,
something?
yeah,
Okay.
yeah. You're 3 slides ahead of me.
Okay.
Yeah, in general, this it might be terrible to what I did in my example was a terrible idea, and I'll tell you because if you so what you're saying here, okay. Here, for instance, I think this is
So as far as I understood, you always, I mean, whenever you try to make some assumptions on these y variables, then you normally always take the extreme case and take the one like the Z2.
So, like if you have normally it's fairly common to get clausal cores. They might be gigantic. Mm-hmm. And if I do this, then I'll, every new core will give me like a linear number of extra variables. That's going to become a pain pretty quickly. It's not impossible to do it in that way, but it's better not to. But let me see, there will be a slide about this. But that's definitely a good point. Where were we? Here. Okay. It was the next slide. So, so for the first core, we just said we added y3 and y4, and then said that they are that y3 greater equal y4. You can do it this way. There is a way to force RunNSat to do this, but in general, it is better to just define, again, by reification, y3 to mean this. I'm actually cheating a little bit. You can be a little bit smarter than this. You should not define y3 in exactly this way. You should use that you know that this is a core. But for the purposes of exposition, this is a slightly simplified version. So you can be slightly smarter than this. But the moral of the story is define y3 to mean this. And then you rewrite the objective with only y3. So now you will no longer have equality, but the rewritten objective is less equal the original objective. Okay. And then if you remembered, at some point we canceled y3 from the objective. At that point, you would introduce that, oh, y4 means that all of them are true. And then you sort of mentally in your head pretend that y4 was there all the time. And you do the bookkeeping needed for this. And this is in general a very good idea.
Isn't it also in general? Because, I mean, if I make assumptions, I would also try the most extreme case first, right? So I would basically say like y3 is equal to 0. So everything to 0. Then I maybe find something that includes y3 in a core, and then it cancels out. And then I can naturally assume, okay, so it cannot be this one. So
yeah, I mean, you're absolutely right that if I define it in this way, and if I assume y3 first, then I would immediately propagate y4, right?
Yes.
I think this is what you're saying. I think that there are some, it's like, it's not immediately, like, I would also say that, yes, let's assume y3 to false, and then just y4 will follow. I'm not sure if reality is that simple, but I agree with your intuition.
Mm-hmm.
But more importantly, you should be lazy because otherwise you'll get too many variables.
Mm-hmm.
One other way, so note that this stratification and also this weight-aware core extractions are actually two ways of when your assumptions are a bit too weak, then you will start getting partial solutions. So then you have a notion of your upper bound. But there's a more systematic way of actually switching between upper bounding and lower bounding search. One that is fairly successful. If you know you have, say you're running in a competition, for instance, then you can do something that's called core boosting. You run core guided search for 10% of your available time, and then you switch to solution improving search. And this can be amazingly good. But this again assumes that you know I'm willing to spend an hour on this. Okay, then you're going to do core guided search for 360 seconds and then you switch. Another thing, if you don't know, is you can do a hybrid search or interleaving search where you just run core guided search, then switch to solution improving search, then switch back. Somehow you manage the time between the two. This has been tried in CNF-based solvers, but it gets fairly messy because of all the rewriting and stuff. In a pseudo-Boolean solving, since you have no messy rewriting, this is very cheap to do. And in fact, this is this interleaving mode in rounding SAT is still like amazingly competitive. There are many other things that I didn't tell you about, such as you can also, we didn't talk so much about phase saving, but if you're in optimization, question is, should you use standard phase saving or should you use, for the objective variables, for instance, should the phase be that you always try to set them to false, or should your phase be like the best incumbent solution so far? You can try to play with different phases. One thing that is important for MaxSAT is that you try to see if my clauses actually encode at most one constraints. In particular, if the objective contains a lot of variables and you know that you have to give up on all of them in the objective except one, then this is interesting to detect. One thing, what if you do core guided search in a pseudo-Boolean setting and I don't want to round to a cardinality constraint first? Well, then things get a little bit messy, but it seems that one of the solvers from Helsinki in this year's pseudo-Boolean competition explored this. One thing that is important that rounding SAT gets wrong is if you're doing weight-aware core extraction and if you're doing stratification, then it's very important when your assumptions are too weak that the solver reports so immediately. Like if your assumptions are consistent, then you want SAT back immediately. Okay. If you accidentally stored a solution improving constraint in your database because you're switching between upper bounding and lower bounding search, for instance, then there's no way you will allow the solver to return until it finds a better solution than the best so far. And that means that there will be no cheap SAT calls. My understanding is that the way they deal with this in Helsinki, they basically have two different solvers, one with a solution improving constraint, one without. It would be interesting to see if there are better ways of doing this. For instance, by reifying, say, a solution improving constraint. One other thing that I wanted to say is the lower bound that you get, we only did this by example, but it turns out there's a paper that I think is worth reading by George Katserelos from SAT, I think last year, that like, what is this constant term that started to appear in the core guided rewrite objective function? What is this thing? And it turns out that you can view it as you take all the counter definitions and you take all the cores that you have found, you view this as a linear program, you relax it, and you optimize. And then the lower bound, so the optimum value of the dual is, in fact, that's the lower bound that you get. And this would require some time to figure out. It's not too hard, but you have to view it from the right angle. Another very interesting thing is that people in SAT solving have been trying to use not resolution, but the so-called extended resolution proof system, which is basically resolution plus the possibility to define new variables that mean interesting things. We know in theory that this is a ridiculously strong proof system. Okay, much, much, much stronger than cutting planes and any other proof system known for man, pretty much. So just running your CDCL solver, but once in a while introducing good reifications, good definitions, in theory, that should beat anything. The trick is like, how do you know what definitions you want and how do you force your solver to use them? Nobody knows. So basically, I think the SAT community has given up on this. But if you look at what core-guided search is, it is actually doing extended resolution where the new variables being defined are defined guided by that we want to minimize an objective. And this is a setting in which extended resolution seems very successful. I think it would be but it's also a setting where the extension variables are introduced in a very, very structured way. So it's not obvious, maybe we could even prove some lower bounds for this. This would be very interesting, I think, from a proof complexity point of view. Putting on my theory hat, just to see how well does this work, the different things we talked about. So here are some, the open source MIP solver skip. Here's the CDCL-based pseudo-Boolean solver NAPS that just translates to CNF. Here's SAT4J. Here is vanilla rounding SAT with linear SAT on SAT search. Here is rounding SAT with only core guided. Here's core boosted, 10% core guided, and then linear SAT on SAT. And then here are these interleaving modes where you see non-lazy variables, everything else. And here is where you have only clausal cores. So you only extract cores that are actually clauses instead of general pseudo-Boolean constraints. And here is like the full-blown hybrid. And you can see for all of these things where like having general core constraints instead of just clausal cores seems to really help. Being lazy with the variables really seems to help. Core boosted, as we can see, is really good. So the benchmarks, the pseudo-Boolean competition 2016 optimization problems, some MIPLib01 optimization problems, some knapsack problems, some crazy or some interesting proof complexity crafted benchmarks. And you can see that hybrid and core boosted are most of the time really very good, except SAT4J is really good at knapsack problems for some reason. And also, depressingly, at the time, Skip was beating the crap out of pseudo-Boolean solvers. Okay. But I should say also, this is not entirely a fair comparison because Skip is a beast. It's using lots of like pre-processing. It's detecting, for instance, if you have a knapsack problem, Skip will detect this and switch to a completely different algorithm that does dynamic programming, for instance. So it's not a fully fair fight. But I think this the point is that this somehow, it's probably fair to say that this was pseudo-Boolean optimization before you took these core-guided things and lifted them to 0-1 interlinear inequalities. And I think it's pretty clear that the improvements are fairly significant. So using core-guided search for pseudo-Boolean solving can really help. And here you see more a cumulative plot. Again, at the very top, you see Skip is winning. but here you see the hybrid mode. You see that stratification and disjoint cores doesn't actually in general help so much, but again, that might be because we're storing this solution improving constraint so that we don't get rounding set to return fast enough. I don't know if I want to say more about this. There's a question.
Yes, I have a question about the time spent to solve the instances. Do you know, because in your core-guided approach, you are adding new variables to the problem. You are also adding new clauses to the problem. So does it slow down a lot the solver? Does it mean that the first iterations are very fast, and then as soon as you add more constraints and more variables, it becomes slower and slower until
it's a great question. Not sure if I know the answer. Definitely, if you're non-lazy with the added variables, that can really kill you. But it's a good question. Like in terms of you could measure things like you could measure conflict speed and these kind of things and see if the conflict speed goes down, but if it still pays off. I have to admit I don't know if we have that data. It's a good question. It's a good question. I'm not sure I have a very good answer. Okay, so I also want to say a little bit about, now we're switching to something else which is called implicit hitting set. We still have the same objective. We still have a bunch of pseudo-Boolean constraints. Implicit hitting set has mostly been done for MaxSAT. So let's think of our constraints as clauses right now, because that's where like the name hitting set comes from. Okay. So as in core guided search, we're going to use the solver with assumptions, and we're going to collect cores. So suppose that we have extracted the following cores from different types of assumptions. We're not going to do any objective rewriting. Same objective all the time, but we're going to run the solver with different assumptions and get back different kind of cores. And now you realize that every core clause here, you can sort of view it as, well, I have to select some literal from this set, right? And set it to true. So really satisfying a bunch of cores is really a hitting set. You have to select a bunch of literals and set them to true. And note that all of these are objective function literals. So all of them have a cost. So this is a weighted hitting set problem, right? So what the implicit hitting set solver does, it maintains some set capital K of core constraints that are constraints implied by the formula and constraints only containing objective variables. And then you run an optimization solver to compute a good hitting set, say an optimal hitting set for now. So again, you pick a bunch of literals that satisfy all the core constraints, because you know you have to satisfy them. They're implied by the formula, but you minimize the cost of satisfying these cores. Okay. And now you know, once you solve this problem, you know that this is actually a lower bound of what you can hope for, because you know you have to satisfy all of the core constraints in K, because they're implied by the formula, and you're doing this in the most economic way possible. So now you ask your solver, you know, it would be great if I could have this assignment. Can you extend it for me to the non-objective variables, please? Okay. So you run the solver on F with assumptions, with all the literals that you actually did not have to set to true. You say, please keep them false. If the decision solver manages to do this, now you know you have your optimum. Otherwise, you get a new core, you add it to capital K and repeat. Does this make sense? And again, you can ask, I think this is an interesting algorithmic idea. It is in some sense, I'm getting a little bit ahead of myself. It is somewhat similar in flavor to something like Bender's decomposition, that is logic-based Bender's decomposition, but I don't know if something like this has been tried in operations research. How would you actually do this in practice? I'm cheating you a little bit. You don't need to solve the hitting set optimally. You only need to find an assumption that, if it worked, would give you a better solution than the best solution you've found so far. So don't kill yourself by solving your hitting set optimally, just solve it good enough. But how do you solve this hitting set problem? Well, if you think about it, this is another optimization problem. It's actually a pseudo-Boolean optimization problem. So I guess, you know, we could run a pseudo-Boolean solver on it, maybe, except that we're trying to build a pseudo-Boolean solver. So I don't know. What people mostly do is they run an integer linear programming solver. Cplex has been popular choice. Maybe you could use local search. Don't know if people have tried this. You just want to find a good enough solution. How would you do this in a pseudo-Boolean setting? Again, the cores now will not be sets, right? But they will not be sums of literals greater or equal 1. They will be weighted sums greater or equal some integer. And a hitting set is just a solution to this sub-optimization problem. So basically, you have your original problem, and then you have some new constraints over objective variables only that you have derived from the original problem. And you're sort of optimizing over this smaller problem, and then you call a decision engine to try to extend this to the larger problem. And this has been tried with quite some success by the Coreo group in Helsinki. By basically, they used I guess I should say a hacked version of rounding SAT as the decision engine, and then they build all kinds of fancy stuff on top. And it works pretty well. So just to make sure we're on the same page, how would this work in a pseudo-Boolean setting? Again, you have K is now not as a collection of sets, it's just a collection of pseudo-Boolean inequalities over your objective variables. And you run some kind of optimization solver to minimize the same objective, but only with respect to these core constraints. So now you find a candidate solution for the objectives. You try to extend it. If you succeed, then you have an optimal solution. Otherwise, if you failed, you get a new core back, which you add to capital K, and again, then you repeat. Okay. And just to see how this would work in practice, as a toy example, still the same objective. First, we have an empty set of cores, and the optimization solver says, you know what, I think we can falsify the whole objective, and I'm satisfying all of K. And then we know that we're going to get this core back, right? Because that's what we got the last time. And now we don't necessarily need to round it to cardinality. I guess we could, but why would we? And now we just say, okay, minimize the objective subject to this. And the optimization solver will say, okay, I guess I'll set x2 and x3 to true, but everything else to false. So then I throw away these true guys. I'm not so happy about them, but I try to keep x1, x4, x5, x6 all to false. And I say, can you extend this to a satisfying assignment? And the solver now says, no, here's another constraint. So we got back a cardinality constraint, it seems. Okay, so now we have a new core consisting of the first core and the second core, and we say, can you please optimize the objective here, subject to these two core constraints? And then we say, well, I guess set x2 and x4 to true, but you can set everything else to false. Okay, and then we say, well, I don't like, these variables so much, but x1, x3, x5, x6, let me try to assume all of them to false and try to extend it. And we know that this is supposed to work because there was a solution with optimal value 6. So the solver says satisfied. Okay, does this make this is I'm going like I guess I did like core guided somewhat in detail. I'm doing implicit but pretty fast, but I hope I get the main idea across. Okay, let's look at again, and I should maybe say that if you read the literature, it's not necessarily the case that these two algorithms are described in this way. I'm very consciously trying to make them as similar as possible to suggest that there are a lot of similarities, but still they're different. So let's look at this. If I get a core like this back, in core-guided search, I will then introduce new variables, except I'll do it lazily in practice. And then in the next assumption, I will ignore all xi's in the objective with the smallest weight in the current version of the objective, because those will get cancelled when I do my OLL rewriting. And to replace those variables, I somehow assume that, well, the current chord isn't more than this. And the way I do this is by assuming the counter variable y3 to false. And I get continuously a lower bound estimate, which comes from the LP relaxation of the cores and the definition of the counting variable. For implicit hitting set, I don't introduce any new variables. I just add C to my collection of cores. And then I don't do any LP relaxation. I actually look at the cores I have so far, and I optimize a Boolean solution to these constraints, minimizing the objective. So the lower bound I get will be presumably, like, I mean, they're incomparable now because I'm picking up my cores in different ways, but the lower bound I get is actually a real 0-1 lower bound, not an LP relaxation. And then I say, great, let me try to extend this to an actual solution. And maybe, you know, I could hope to be luckier because this is in some sense seems more realistic than saying that the LP relaxation is closer to the optimum. Although who knows? Okay, does this make some sense? Interestingly, implicit hitting set and core guided perform well on different types of problems, for MaxSAT at least. If you have many different soft clauses with the same weight, then core guided seems to be really good. If you have many distinct weights among your soft clauses, then implicit hitting set is usually better. It would be really interesting to somehow sit down and do some proof complexity here and understand and compare these algorithms. There's some work on this that is in some sense related on different MaxSAT proof systems, but I think there's lots of work that needs to be done, especially on proof systems that really capture sort of what happens in practice. Okay, we're close to the end. I tried to suggest that somehow core guided and implicit hitting set are similar but different. Can you somehow marry them? Okay. Well, here's one idea. You can run your solver with assumptions and you collect cores. This is now we're in MaxSAT. And then every once in a while you identify interesting literal sets. An interesting literal set could be the literals in a core, or maybe it's a set of literals that has appeared in many cores. And then now you're not going to do any objective rewriting, but suppose you would have introduced those counter variables, like as in OLL rewriting, except that you don't do the rewriting. Now you solve the weighted hitting set problem over the core variables plus over these definitions of counter variables. Okay, so that once you've optimized your cores over your cores, you will get some propagation for the counter variables. In particular, some counter variables will go high and say, yes, you have to pay so much here. Okay, but all the counter variables that didn't propagate to true, you'll now in your next round, you'll assume as before, my assumption is the optimal solution to the hitting set. Plus, in addition, you force all the counter variables that were not propagated to 1, you force them to 0. So this is morally some kind of trying to get the best of both worlds. And this is known as abstract cores or MaxSAT. To the best of my understanding, we don't have this for pseudo-Boolean solving, and it's not even entirely clear how you would do this. I think this is another, like doing abstract cores for pseudo-Boolean solving would be super interesting. Okay. Okay. What could we, what's some open problems, or what are the sort of future prospects of pseudo-Boolean optimization? Well, the first thing is, I think, to try to communicate that pseudo-Boolean optimization solvers exist, because I paid a special attention to this at the SAT and CP conferences this year. And every time when people have some interesting MaxSAT application, there are sort of two steps. They write their problem in a very nice way to a 0-1 integer linear program. And then they say, oh, I want to use MaxSAT on this, but I don't have a CNF formula, unfortunately. So then they hit the literature hard and somehow try to rewrite to CNF, and typically spend some part of the paper explaining that, oh, this is tricky and how to rewrite this seems to influence the result quite a lot. And you sort of want to ask them, well, did you consider that? Don't do the rewriting. You have a perfectly fine 0-1 integer linear program. Just run a pseudo-Boolean optimizer. And the reason people don't do this, I think, is because they don't know these tools exist. That's the first challenge. But it's not as easy as this. We know also that this re-encoding can give you extra power for the auxiliary variables. And also, since it sort of, pragmatically will be the case that there are tons and tons of problems with people who don't maybe know that much about SAT, but at least they know how to encode their problem into MaxSAT. Okay. So, pragmatically, there will be tons of MaxSAT problems out there. Could we somehow build better pseudo-Boolean solvers for these MaxSAT problems? One thing that you would like to do is what we also came up before lunch. Could we somehow rewrite the problem when, in fact, there are a lot of clauses that encode some cardinality constraint, for instance? Could we detect this somehow? In fact, we had a paper on this a few years back, which seemed really, really promising, but we never got it far enough to actually put it into like the main branch of rounding SAT. I think MaxSAT optimization would be a very interesting potential application for this on-the-fly cardinality detection that we had. And then one thing that I think is really, really interesting is, would there be a way to present implicit hitting set and core guided and solution improving search and maybe branch and bound in such a nice general framework so that you could seamlessly switch between, do a few rounds of core guided, then a few rounds of implicit hitting set, then a few rounds of solution improving search, and then switch back, because we know these different approaches have complementary strengths. And the way it is now, we do know that there are hybrid modes between, say, core guided and linear search, or implicit hitting set and linear search. But for instance, core guided versus implicit hitting set, once you've started your core guided algorithm, it's going to start to rewrite the objective. And you're going to introduce new variables, so your cores are going to diverge. So then what would it mean to switch to implicit hitting set later? Or if you started with implicit hitting set and you collect a bunch of cores, then when you want to switch to core guided, it's like you can't do the OLL rewriting because you didn't pick up your cores in a structured way. It would be really interesting to think about whether something could be done here. There is a paper that tries to give sort of a unified description of this, these different approaches, but you have to instantiate it and say which algorithm you want, and then you cannot switch. And I would like something that would allow you to switch dynamically. And final obvious question, which we'll return to after the break. There's so much nice ideas in the operations research literature. Could we somehow maybe take some of those ideas and use them in our setting? Okay, so this ends the pseudo-Boolean optimization tutorial. We talked about MaxSAT and so that there's core-guided solving, implicit hitting set, and there you could also use integer linear programming to solve the hitting set problems. We know that these are complementary approaches, so there should be room for exploiting synergies. Also, lifting all of these approaches to the pseudo-Boolean setting is interesting and seems worthwhile. It gets a lot simpler because a lot of the pain of the MaxSAT papers is you have to do all of these re-encodings to express things that are pseudo-Boolean. And then when you read a MaxSAT paper and want to do it in a pseudo-Boolean setting, mostly you just say, okay, fine, I don't need to re-encode. All of these constraints are native. Okay. But it's not quite that easy. I mean, pseudo-Boolean solvers are slower than CDCL solvers. And again, we had this problem that suddenly you get much more design choices, which directions are good or bad. But I think there are many interesting and unexplored questions, which means that you can do a lot of fun research and maybe find some low-hanging fruit. So. Okay, any questions on this?
Well, I will repeat this tomorrow, but I would also include MaxCDCL in the equation of combining correlated and implicit hitting set, because it's also kind of related.
Absolutely, absolutely. Yes. Sorry, I said
No,
before, this slide was
There's no need. I just wanted to comment.
Yes. So
Actually, I will explain
tomorrow.
tomorrow what are the relations.
Yes.
And maybe also for the implicit hitting set, it kind of requires always that you can solve the reduced problem, so to say, with only the cores like very quickly, right? So this is mainly the reason why I use like in MIP solver or so. But this kind of like, I mean, the chicken and the egg problem, right? I mean, you want to solve it actually with pure approaches of pseudo-Boolean optimization. I mean, I don't know. It's really a question. It's just like it sounds a little. Because I mean, you leverage the power basically of MIP optimization, but
I'm not sure. Like I think nobody knows why we're using a MIP solver for the implicit hitting set, and I think it just seemed to work.
Okay.
And also, when you move into the pseudo-Boolean setting, then you don't even have, like, you no longer have a hitting set, right? Then it's very clearly just a pseudo-Boolean problem, but a pseudo-Boolean problem with a special property that the objective contains all variables in your instance. This is all you know.
Yes, but if you try to solve, for example, with pseudo-Boolean optimization, then the question is again, how do I solve this problem like properly with pseudo-Boolean optimization? Then I could again use a solver with I don't know, with a core-guided approach, because it has a right?
Yeah.
I mean, it's like,
or a local search solver, maybe. I don't know.
Yes. Okay.
Okay. Good. So then I think we're taking a break here.